Welcome everyone. Thanks for joining me today. This is right before lunch. I hope that it's interesting enough for you folks. Hopefully you are not too hungry. So the topic for today is Grokking event system in Python. It will be more of event system than Python, but hopefully that is alright for you guys. So to set the base for the discussion for us today, to set the base for our discussion today, what is an event-driven system? So three main components. First is the event producer. Second is the middleware layer to stock all of the events, a queue or stack or whatever. In the real world, you may encounter RabbitMQ, Kafka, whatsoever. And then you have the downstream components to consume those events. So three basic core block components: event producer, event storage, and then the event consumptions. You may want to keep in mind those three components because we are going to reuse all of that very soon in the next slide. And to draw some kind of similarity or difference between the event-driven system and a normal web app architecture is that in API or synchronous events, you have guaranteed processing of your request. So you send a request after a short period, usually in HTTP, you have 60 seconds of timeout, and you have instant response or result of the request. But here, it may not be the case, which typically arrive to the complicated problems or challenge that we have to deal with is latency. Whenever you send a request, you need to make sure that your request is sent properly and then processed properly in a reasonable amount of time. What we want to avoid is the kind of architecture that send the events and you have to wait for a long time to get the feedbacks, or maybe not feedback at all. Just like the tax office, for example. I sent my request for refunds, 6 months later, still nothing. So hopefully we design a better system than that. And the second challenge in an event-driven system is the consistency. In many cases, we don't have to worry about the causality relationship between your events, but in some cases, it really matters. Let's look at this example here to simulate a small banking transaction system. If we decouple a simple banking transactions into events, the first event would be, I want to put 10 euro in my bank account. And then a second event must emit to subtract 10 euros from my bank account and then deposit that 10 euros to my friend's bank account. And you see those three events has causality relationship, and they need to be processed in the same order as they emit and arrive. Failing to do that, we would end up in the tricky situation that my bank account starting at 0. The first event I get is to subtract 10 euro from my old banking account, which means, well, that's not really nice. The final challenge, well, not the final, but one of the final challenge that I want to discuss today about events processing is the retry and error handling logic. Because if you just look into that system, especially when you have causality relationship between events, event retry becomes a little bit tricky because you have three events which need to be processed in the same order. And somehow the second event receive failure when you try to process it. So now you come up in a tricky situation. Do I go forward to process the third event, or I just stuck there? Well, if your event has a FIFO causality relationship, you can't go forward because that would break the consistency of the system. But if you can't go forward, that means you are stuck and the whole system becomes stuck. And maybe that was what happened with my tax refund request that I sent 6 months ago. It's just stuck somewhere, the whole system just gets stuck, and that's it. Yeah, so sum up, three main challenges. First, the latency and the performance. Second challenge, the consistency of the system, and the third challenge, like the error handling, how do we retry those errors. And we are going to look quickly into common patterns of how to deal with those errors. But even before looking into those errors, there is one point I missed. I just want to clarify one thing, is that when you look globally into an event-driven system, the main difference between that and a traditional API or synchronous system is that the model of the world is no longer the state of the system. If you look into an API, let's say a RESTful API, when I want to update the name or the descriptions of my bank account or my account name, I am sending the new update, the new state to the system, so that the new system receives information, update it in the database. The same thing happens over and over again for all resources. But in the event-driven world, we don't send explicitly the state. We send the events that when they are applied successfully, we can deduct the state out of it. So the modeling of the world is different. You may keep that in mind. It could make things easier to design, to reasons about all of the future event-driven system that you are going to build. So back to the solutions, or I would say the patterns that we can use to overcome the challenge we face in event-driven system. The first challenge I mentioned is latency in optimizations. To optimize an event-driven system, there are two distinct directions that you need to take care of. The first is how you are going to accelerate the event reading speed, and the second is how you are going to accelerate the processing speed. Why two distinct directions? Because in a normal API, usually the API is designed in such a way that the processing should be lightweight and really fast. So you don't have to worry much about the processing. You just optimize the processing of the API, increase the throughputs, and that should be it. But let's take an example of a typical event-driven architecture, which we see very often is that, let's take Amazon for example. When I add an item into my shopping cart, it sends an event to likely a recommendation system, a machine learning system behind the scenes that will trigger, process a bunch of different algorithms, and then give me the recommendation in real time. Which items should I look into further to add into my shopping list? So you can see event-driven systems are usually used in case when processing is a little bit more computational heavy than API. So you invoke a model, you invoke a machine learning algorithms. Those kind of things makes this a big requirement for event-driven system to optimize for both reading speed and processing speed. To optimize for reading speed, it's actually a trivial problem because optimizing for reading speeds we have done for decades with API. Starting from Python 3.5, we have asynchronous programming included directly into the native package of Python. So if you look at the schema on the right, how asynchronous Pythons or asynchronous programming in general happen is that you dispatch a request to fetch the data somewhere, usually on a remote server, and without waiting for the actual result to come, the program, in this case the Python program, can switch to other tasks so that it doesn't have to wait for the result or stay blocked forever. So you look on the schema on the right, I send a request to fetch data, in this case fetch an event from a remote server, and without waiting for a result I do something else, or maybe I can start fetching other events. So the whole thing, asynchronous programming, can happen in a single thread. You don't have to add more processor or whatsoever. Everything happens in a single thread, which is convenient. And that's really easy to use. If you look a little bit on the example on the left, well, the code is kind of long and we are hungry, so just don't read that. You can just see that there are keyword async and await, which means in Python it indicates when I declare a function async, which means I indicate to Python that you can interrupt the running of that functions whenever you see that it is waiting for result from a remote server. And when I declare await, I mean, well, whenever you get the result from the remote server, just go back to where you left. And simple as that. It comes from likely, I guess, JavaScript. And in Python, starting from 3.5, it's native and it accelerates a lot of reading speed, because when you fetch an event from remote server, likely you get stuck because of the packages traveling all over the globe from all of the undersea Atlantic cable. I don't know where it is, but it's I/O network to be optimized for. But then come to a tricky situation when we have to optimize for processing speeds. If you look into that simple example, here is the example that I want to calculate the pi number. I don't write that, it's ChatGPT who wrote that, so I'm pretty sure it's optimized. But the main point here is that this program requires CPU clock. It's a little bit low level, but it's tapped into the clock of the CPU, do computational heavy. It doesn't require external communication to the external world, but only the CPU power. There is one thing in Python which is called global interpreter lock, which dictates that if your program is using CPU, then only one program or one thread can run that part of code at a single time. So what we think when we have multiple threads running Python is what we think on the left is that, well, I just have one thread to process one message, other thread process other message. But in reality, due to global interpreter lock, what happens is the things on the right you can see here is that, well, only one single thread can acquire the lock to execute your processing program, which requires CPU power, while the other actually have to wait. And to be honest, there is no way, at least with Python native, to overcome that global interpreter lock, because it is how it is designed. So yeah, it's kind of tricky, global interpreter locks, especially when you need to do processing, computations and stuff like that. We don't usually see that with API design, because usually in our API, we don't do computation heavy stuff like that, like calculating pi or doing like tree graph traveling, complicated machine learning program. We don't do that in the API, but in the event-driven things, we have to. So how are we going to optimize for processing speed? It's a little bit more complicated than that. First, the logic is that you would have to run multiple processes of Python, because each process can have one single global interpreter lock. But I don't recommend you to do that, because running multi-processing Python is not easy. It's maybe way harder than it looks, and running productions require careful tunings of the system. And still, even if you do that, you are still blocked by the capacity of your hardware, because one process requires one CPU core. So if you have if your CPU has 4 core, which is usual, you can only run 4 processes and no more than that. So that is not typically good. That is not typically how we want the system to scale. And what I actually recommend is that, first of all, we should containerize your applications. When everything is container, you can just spawn up, like I do usually, one new container in production and one new container, really lightweight container, which may require only a fraction of CPU or 64 megabyte of RAM, which is really lightweight, throwaway container, and one container run one single process with asynchronous programming. So with one container running asynchronous programming, it can already process a lot of I/O connections. And when you add more container, you add more processing power, and everything remains a single process, single thread, very easy to reason about, and you can control precisely the scale of the application by just adding more container. If you have Kubernetes cluster, that is even greater. You can just add more pods, which is easy, or you can use like horizontal scaling in Kubernetes, which is great. But in general, the configuration I use and I recommend is one container. Each container use asynchronous programming and just add more container whenever you need. Now, when you add more container to process event from the queue, the tricky problem arrives because your queue may have strong consistency in FIFO orders. Just take back the example I had from the banking system. But when you add more container, you are no longer in control of what message get processed first, because each container lives its own world, and you have absolutely no control, and you will easily break the consistency of your system. So your system must have FIFO order of the message and also FIFO order of the processing of the message. So how are we going to achieve that with multiple container consuming message at scale? One solution that I do very often is that I have to look at the global architecture of the system. So we won't be able to achieve that easily with just twisting the program or writing better Python codes. That won't happen. But globally, when I want to achieve FIFO order and guarantee strong consistency of the processing, I need not to only scale the container, but I need to scale the queue as well. Why so? If you look on the left, I make sure that one queue is consumed by one and only one container. That's logical, because if one queue is consumed by one container, then you are pretty sure that the message will be processed in the same order as they store in the queue. And adding more queue means you can add more container along the lines, which means adds more computational power. Of course, it adds more cost, but it guarantees very strong consistency. Or another variation is the variation on the right. If you're concerned about the number of containers you may add to the system, you may be a little bit frugal about that, and you can say, well, one container can consume messages from two queues. It doesn't matter. As long as there are enough containers to process the message, this is okay. And as long as you guarantee one queue is consumed exactly by one container, you should be okay, because if the message coming to the queue is FIFO, and if you guarantee one queue is consumed only by one container, it's easy to reason. Everything will be processed FIFO. I just mentioned that guarantee strong consistency in an event-driven system require that you need to process messages in the same order as they arrive, and also here you need to guarantee that the message should be sent in the same order as well, because if you look into the system we add more queue. I mean, previously we had only one queue. Whatever we send, if we send in the right order, it will arrive in the queue in the same order. But if we have more queue, well, it becomes tricky, because let's say all of the events of my banking transaction is dispatched into two different queues, then I mean, there is no way I can guarantee that the FIFO consistency is guaranteed in both queues. So the tricks here is that you need to add one more component, which is called the queue selector. So, or you can say a sticky queue, or any other language. But the main idea is that you need to make sure that all events which have causality relationship should end up in the same queue. One trick I do very often is that I just use a very simple algorithm, which is the modulo. Let's say the category, the key is the user ID. I just use modulo apply on my user ID along to the number of the queue. Then that way I can make sure that all events which belong to the same user ID end up in the same queue. So say we have two queues and my user ID is 3. So whatever message coming with user ID 3 should arrive to queue 3 modulo by 2, which is 1. It's deterministic. So that's why I guarantee the system. But if you have like automatic scalings of number of the queues when you are in a tough spot, you need another more complex algorithm to do queue selector and stuff like that. But the main point is that if you look a little bit online, you will find it. Those algorithms are not rocket science. It has existed for years. So the last topic, error handling. When you do error handling, as I mentioned above, if we have one message, let's say message number 2 here, stuck in the processing, And if you just stop the processing, then the whole system becomes stuck. And to overcome that, you would need another complexity layer, which means here you can see you need to add another secondary queue so that you just keep consuming, but all of the messages that belong to the let's say to the user ID which gets stuck, you delegate to the secondary queue so that it can be retried later by another process, and you just keep consuming other messages. So whenever you have an error, delegate it to an error handling queue separately and just keep consuming. And that's the technique I also use often, and it's actually good. So, yeah. So to sum up, what we have discussed a little bit about event-driven system, a little bit about asynchronous programming in Python, but more importantly, after 6 months, if you ever try to remember about this talk, the key takeaway is that when you design an event-driven system, you need to look a little bit further, global, to the bigger scope of the system. So, yeah, thanks for listening. It's time for questions, I guess. Yes, please.
So, in real-world examples, for example, banking system, you have thousands of events.
Yes.
Some of the events are not firing like we're supposed to because of the development.
Yes.
So, for example, developer made a bug or issue, and for example, specific event that's supposed to fire like that is not firing anymore, and the developer has to go sometimes look into this. But imagine if you have thousands of events.
Yes.
That's just you need the dashboards. You need
yeah, true. It's to answer that. There are multiple layers. So first of all, we can't say that enough. But well, those kind of things are breaking chains, and breaking chains we need to minimize. But it does happen, and when it happens, in reality, usually we have something. If somehow we have like Kafka, for example, Kafka is the kind of event that has its own memory, so that when the event arrives to the system, it doesn't just go away right away. It gets stored right there, so that you can replay history. When the bug is fixed, you say that the bug has been introduced to production like 3 hours ago. You just replay history. That's one thing, and the second thing is that just to minimize the whole things, to minimize the breaking change, we can do progressive rollover and a lot of techniques like that. So yeah, and in general, debugging an event-driven system is trickier than a normal synchronous programming, but it follows the same principle. Any other question? Yes, please.
One question. Do you use like message queue or Kafka topic, whatever, instead of introducing additional worker, which would be like orchestrator or retrier?
Well, yes, in reality, I use both. Previously, Kafka and RabbitMQ, and but the workers are separate because the workers are the consumers that you need to spawn and scale yourself. And scaling the Kafka thing, it's completely different. And regardless of the case, you need to scale up the worker. And let's say, for example, in the case of Kafka, the number of workers you can scale per Kafka topic per partition should follow the same principle if you want to guarantee strong consistency. For example, in my case, I usually have one consumer per Kafka partitions.
Yeah, but I mean for failed messages or whatever, do you send them to separate queue?
The failure?
Yeah.
Oh yeah, the failure could be, in case of Kafka, another topic, for example. Or in case of RabbitMQ, just create a new queue. But let's take Kafka, for example. If you have Kafka topics, bind transaction, you can create another topic which is called bind transaction retry failure. And it follows the same principle.
Okay.